If you're into AI agents, then stay tuned, because in this video, I'm going to be doing a technical deep dive on a custom web search agent that I've built that is 100% local using Ollama and the Llama 3 8 billion model. The GitHub repo containing the code for this project will be available to you, and its links in the description for this video. So if you wish, you may pull that up to help you follow along with the video. I'll start the video off by taking you through a schematic diagram of the agent to give you a high-level understanding of how it works. I'll then jump into the Python code. And lastly, I'm going to demo the agent so you can get a feel of how well these agents work with open source models. If you stay tuned to the end of the video, I'm going to be giving my thoughts on how this custom web search agent can be improved and what I'm planning to do next on this custom web search agent. So stay tuned to the end to hear that. If you're into this content, give us a thumbs up. Don't forget to subscribe to the channel and let us know your opinions in the comment section. Let's get into the technical details. Let's have a look at the overall high-level schema for this agent or this web search agent that I've developed. So the first thing is you get a user query in, and that user query can be anything that requires information from the web. The first step is to actually go into a planning agent. And what the planning agent does is to break that query out into some questions that need to be researched in order to get the answer to that query or to respond to that query. So it's important to note here that the planning agent doesn't answer those questions. It simply proposes some questions that need to be answered in order to respond to the query. The next thing is the web searcher. So the web searcher is a tool that takes as an input the questions from the planning agent and returns a search engine results page from which it then takes the best result from the search engine results page and then scrapes the content from that page and presents it as a dictionary. So what's good about the web searching tool is it will actually present this dictionary with the source and the content of that source of information. And that's key for the later steps. And then we have an integration agent. So the integration agent takes that information produced by the web search tool, so the research produced by the web search tool, and then there's a decision step here. So it decides whether the information is sufficient to answer the question, which is obviously the initial user query. If it's sufficient to answer the query, then it will proceed to the next step. If it's insufficient, then some feedback is provided, and that's stored in a short-term memory JSON file. And that feedback is then provided to the agent, the planning agent, which then repeats that process from here. So there's a feedback loop here. This is the first feedback loop. If it is sufficient to answer the question, then we move on to the next agent, which checks the response. So it's checking the response for mainly formatting things and coherence. If it meets the criteria, then we provide a final response. If it doesn't meet the criteria, there's a reason that is provided for why it didn't meet the criteria, and that's sent back to the integration agent, which will correct the response in order to provide a response that meets the criteria we need. That's the overall agent schema. It is fairly simple. This is going to be available to you in the GitHub repo, so don't worry if you didn't get that right now. I think when everything comes together, it will become clear how this agent works. All right, let's start looking at the Python code to see what the web search agent does under the hood. Let's start our deep dive on the actual Python code behind this agent. So the Python code consists of 1, 2, 3, 4, 5, 6 main files, right? So a few of these are actually setup and configuration files. So requirements.txt obviously is to install the libraries we need. We have the memory.json, which obviously stores the feedback as shown by the schematic diagram. We have a config file that keeps our API keys. So we won't be going through those. The files we'll focus on are prompts.py, agent.py, and search.py. Now, this is fairly similar to some of the other agent videos I've done, so specifically the custom agent video. So if you have watched that, feel free to skip ahead straight to the demo if you wish. There are some things I've implemented slightly differently here, so you may want to continue to watch, even if you have watched my previous custom agent walkthrough. Okay, so starting with the prompts.py, and as the name suggests, this is where we actually keep all of the prompts that power the agent. So we have a prompt for the planning agent. We have a prompt for the integration agent. We have a prompt for the agent that's responsible for checking our response to make sure it meets certain criteria. We have a prompt for the search tool. So this actually helps us identify the search request based on what the planning agent suggests to then use in our search tool. So this is what this does. And then we have a prompt to identify the best source from the search engine results page. This is what get search page prompt does. So there is a lot of information here. And part of the reason there is a lot is because using local models, you have to be really specific with how you prompt a model. So they're not as good at reasoning as some of the proprietary models. So for example, even GPT 3.5, GPT 3.5, you can get away with slightly less prompting than if you are using an 8 billion model, for example. So this is why the prompts are quite lengthy here. So I'll talk through them and give you an idea of how these prompts work. So for the planning agent prompt, you are an AI planning agent working with an integration agent. Your job is to come up with questions you need to answer the query. You must not answer the questions, only generate the questions. So I was finding that if I didn't add this line in, the agent would actually start generating responses or answers to those questions. So I had to specifically tell it not to answer the questions. If there are multiple questions, highlight the single most important question to answer. Ensure your response takes into account any feedback if available. So here are the outputs from the tools you have used. Here is your previous plan. Here is the feedback. You must carefully consider the feedback and adjust or change your plan based on the feedback provided. For example, if the feedback is that the plan is missing a key element, you should adjust the plan to include that key element. You should be aware of today's date to help you answer questions that require current information. Here is today's date and time. So that's in the UTC time zone. Just a quick thing here on the outputs. These are the outputs from a previous run. So I gave the outputs to the planning agent to give it context on what information had already been retrieved so that it could generate a plan based on it without kind of duplicating information that it already has. So that's the idea behind it. So we'll leave it in there and just see how it works. Okay. So let's move on to the integration agent. You are an integration agent working with a planning agent. Your job is to compile a response to the original query based entirely on the research provided to you. So the research is obviously the information provided from the WebSearch tool. If the research is insufficient, provide explicit feedback to the planning agent to refine the plan. This feedback should include the specific information that is missing from the research. Your feedback should state which questions have already been answered by the research and which questions are still unanswered. If the research is sufficient, provide a comprehensive response to the query with citations. In your comprehensive response, you must do the following. 1, only use the research provided to generate the response. 2, directly provide the source of the information in the response. The research is a dictionary that provides research content alongside its source. Let's get that right. So then we give it the research, and that's the outputs. We give it the plan from the planning agent. We reiterate, you must fully cite the sources provided in the research. Right. And then we give it the sources from the research too. Do not use sources that have not been provided in the research. So I was finding that the model was actually hallucinating sources, which is no good. Obviously, we don't want it to do that. So having this in helped to prevent it doing that. So then we give an example response. I'm not going to read through the example response, but it's just to provide the model with an idea of what type of format we're looking for. Then we talk about the quality assurance process. So there is a quality assurance process to check your responses meets the requirements. Response meets the requirements. Here are the results of the last quality assurance check. And then we have the reason. So the reason is the result of the last quality assurance check. So that's the reason why I was rejected. Take these into account when generating your response. So here are all your previous responses. So that's obviously coming from the memory.json. And no, previous responses. Yes, yeah. So apologies. Yep, the previous responses are coming from the memory.json. And here is today's date and time. So we give it the previous responses so that it has an idea of things it's already said. And this is particularly helpful in multi-hop questions. So we don't actually like miss out information that we need to answer a question. So feeding back the previous responses into the integration agent is useful for that, especially with multi-hop questions. And if you don't know what a multi-hop question is, I will explain later on in the video when we go through some examples. Actually, in the schematic diagram, I think I probably have missed this feedback loop in because we should be feeding in previous responses into the integration agent. I'll update that in the GitHub repo so that when you look at that, it does have that feedback in. And then we give it an awareness of today's date and time. And that's important for asking questions on current events. It gives it a reference point to be able to work from. And then we have the final three prompts, which are a little different because what we're doing with these final three prompts is we're actually asking the model to return a response in JSON. So the first one is to check the response. So remember, after the integration agent produces an answer, we send it through to be checked by a kind of quality assurance agent, if you want to call it that. So there's some criteria that we want to meet. I'm not going to go through the list of criteria, but one of them is making sure that the response has citations and sources. So then we want the model to return this JSON. And what we have here is pass true or false. If it's relevant, irrelevant or not relevant, coherent or incoherent, comprehensive, and then citations. And then we have a reason. So that reason is fed back into the integration agent, as you saw in the schematic diagram, to tell it, okay, you need to adjust one of these things. And then we have generate searches prompt. So this is obviously taking the search engine results page. Apologies, no, this is taking the response from the planning agent and then turning that into a search engine query. And then we can feed that into the functions we need to actually generate the search engine results page and scrape that page and so on. And then lastly, we have the get search page prompt. And this takes the best URL from the search engine results page. So we're actually asking the model to decide from the search engine results page, which provides not only the URL source, but also a description of what's on that page, what might be the best source of information to answer the user query. And we return that as a JSON. So this is what we'll get as a response. Before I move on to looking at the search.py file, I do want to just step back here and probably get rid of, in fact, I will get rid of this line for outputs because I think it is superfluous. The reason being is we are getting feedback from the integration agent, which will give us an idea about, what information has already been included and what information is missing from our planning agent. So I don't think we need to give it and the outputs. I think this is kind of wasted context here. So I will get rid of this. The feedback from the integration agent should be enough for the planning agent to develop a sufficient plan. Great. So we have covered the prompts.py. The next step is to cover the search.py. So I'll be stepping into that and showing you how that works. So let's step into the search.py. There's a helper function up here just to load in our API keys. And then we have this class, which is the web searcher. And there's various methods in this class that enable us to search the internet using a search engine, return a search engine results page, and from there, select the best page and scrape that. And the prompts I showed you earlier in the prompts.py file help to do that. So this project does work with Ollama. As I said, it's a local project, but it also works with GPT 3.5, GPT-4, so all the OpenAI models, and it works with your own hosted server too. Okay, let's explore some of the methods here. So the first method is obviously to generate the searches. So how we're generating the searches is we're taking the plan from the planning agent and we're calling the model to generate that search. So we give it the prompt, and you can see that prompt here, the generate searches prompt, which is coming from the prompts.py. And then we provide a response. And that response is just going to be a search query that we put into the search engine. That's all this function is doing. So our generate searches method is simply taking our plan and turning it into a query that we can run in the search engine. So the next step is to get the search page. So once we have used our search engine, what's going to happen is we're going to return a search engine results page. So we actually need to select the best page from this search engine results page. And we do that by using this get search page method that I've written. And the prompt here is the get search page prompt. So remember, all of these two prompts, the get search page and the, sorry, not these two methods, so the generate searches method and the get search page method all return a format in JSON. So that's why we specify the format as a JSON. And what this is going to do, the get search page will take that search engine results page as an input, and it's going to give us the best page based on this prompt. So this prompt, remember, takes the search engine results page and gives us the best source to investigate from that page. That's all we're doing here. And the response for this is a search page URL. So it's the best source. And we'll take that later on, and we're going to actually go ahead and scrape that page. So this method does what it says on the tin. We're fetching the search results. So this is where we're actually using our SerpDev API. So the SerpDev is Google search engine results page. We make a call to that API to fetch the best, sorry, not to fetch the best, but to fetch our search engine results. And that's based on the search queries. And those search queries obviously come from the function here, the method here at the top, which is generate searches. So that's our search query. So that's what we're doing here when we're fetching our search results. And then we want to also scrape that data. So once we identify the best URL from the search engine results page, we put that in to the function, and this function scrapes the website for the information and returns this dictionary where we have the source, and that's the website URL, and we have the content. So the content is maxed out around 5K words. Obviously, if you're working with this yourself, feel free to come and change this. Depending on which model you're working with, the context, you want to be aware of how much context you're actually putting into the model. I think Llama 3 8 billion has a context limit of around 8K tokens. So just be aware of that. You can't, it's not unlimited context. So that's why I've put I've limited it at 5K words. So at the end, you're going to get this dictionary returned where you have the source, and that's the website source, and the content, which is the content of that website. So just to warn you ahead of time, this website scraper method is not the best. Sometimes it actually scrapes websites where the content is unreadable to a large language model. And therefore, I've implemented this function here, which basically identifies whether this is garbled context. So that's content that's unreadable to a large language model. So what I've done here is based on a certain threshold, and that threshold is determined by the ratio of non-ASCII characters to the length of the entire text. So if it is above that ratio, this is garbled thing is true. And then when that happens, what we do is If it's the case, we print failed to retrieve context, and then we identify what the failed source was, and it's because it's garbled text, and then we append it to a dictionary of failed URLs that we tried to scrape from. And that helps later on implement a retry method where we don't use these URLs that are in this failed URL dictionary. So that's the retry method, and that's how I've kind of implemented a mechanism to make sure that when we are scraping content from the internet, that we're actually able to scrape content without just entering a loop of errors where we're just pulling out content that is unreadable to a large language model. It is rudimentary, but it does work well enough for what I needed to do for this web search agent. And there is a similar thing here if we just retrieve an error from trying to scrape the website. So obviously, sometimes you can just get an error. Sometimes it's an access error or something like that, where you just, for some reason, you can't scrape that website. We have that same mechanism to identify when a website is unscrapable, and we append it to a dictionary of failed sites. We bring it all together using the use tool method. So the use tool method starts off by generating searches. So we have our search queries here. And then we fetch search results. So that is using the search engine. And then we fetch search results. So that's using the SERPer tool. And that returns a search engine results page. Then we identify the best page. So we're putting out the best page there. And then we are scraping that content. And once we scrape that content, we enter this while loop. So if response is false, if we are unable to scrape that content for one reason or another. So that's whether the content returns garbled context, so it's illegible to a large language model, or we fail to scrape that content, we enter the while loop, and I've set it to a maximum of 3 attempts. So it will attempt to retry by getting another page from the search engine results page and then scraping that one. So it won't redo the search. What it will do is it will look at the existing search engine results page that we returned and try to select a different page to scrape. So that's how we implement that retry mechanism. And that is pretty much it. We return all of these to print. If you don't want to return all of this stuff, you can set this verbose variable to false, and you won't return all of the additional content from using the tool. That's it. Let's move on lastly to the agent.py to see how we bring everything together into the agent workflow. Let's move on to the final file, which is the agent.py file. And this is where we're bringing everything together to create this web search agent. So first of all, there is a load of helper functions in here. You've got load config, get current UTC date time, which is self-explanatory. The load config stuff obviously brings in the API key. And then you've got these helper functions: save feedback, read feedback, clear JSON file, initialize JSON file. All of this stuff is basically to save, create, and read the JSON file, which is obviously memory.json. Just to show you how that looks, it's blank right now. But that's all this stuff is doing at the top. So those helper functions, don't be too intimidated by that. That's all it's doing. It's just helping us write to the memory.json, read from the memory.json. And then once we've delivered our final response, we clear that memory.json. So it's just helping us manage that short-term memory. Then we can step into the agent class itself. And there's a load of things up here that just help initialize that class. The class is actually quite basic when you get under the hood. It's just a few methods, the first of which is to run the planning agent. And we discussed earlier we discussed by looking at the schematic diagram, and you've seen from the prompts.py what the planning agent does. Here's where we read in the prompt for the planning agent. So we read it in as a system prompt. And all the variables we need to make the planning agent are read in and formatted as a system prompt. And then it's basic. It's just a call to the large language model of our choice. So because we're using Ollama, we make the call using the payload here. And then we return a response. And remember, the planning agent is going to come up with a series of questions, or come up with some questions that we need to ask in order to answer the user query. So that's all we're doing here with that method. Next one is the integration agent, and it's a similar type of exercise, except the prompt is different. So with the integration agent, we're using the integration agent prompt, which obviously is doing a few things. It's either providing feedback if there's not sufficient information, or it is actually providing a final response to our user query. And we're doing exactly the same thing because we're using Ollama. We're using the payload in this structure. And we're returning a response. And then we've got our check response. So the check response is slightly different in that when we run the check response method, we're actually returning a JSON. So we've got the format set to JSON. And remember, what the check response does is it checks the response from the integration agent and ensures it matches the criteria that we've set. And that criteria is obviously outlined in the check response prompt. So don't be too confused by that. That's all that's happening there. The criteria is outlined in the check response prompt. And because we're using Ollama, we're doing it in this way. And then we return a decision dictionary, which then we can use to decide whether the response is appropriate to actually deliver the final response, or whether we need to actually enter that feedback loop. Okay. And then lastly, we have this execute method. And this execute method is how we actually put everything together. Within the execute method, we actually decide how these agents work together. So I've defined a deterministic execute, deterministic agent workflow. And this is how we do it. So while this criteria is not met, so meets requirements is obviously the requirements of the agent that checks the response. So while that is false, and also the number of iterations which we set is under the maximum number of iterations, the first thing we're going to do is we check the feedback file. So obviously, for the first run, the feedback file will be empty, so we won't return any feedback. And then we come up with a plan. So we do that by running the planning agent, right? And the planning agent will take its previous plan. So on the first run, the previous plan is obviously empty. It will also take its query from the user and the feedback, which will be empty on the first run. Then we take that plan and we use a tool. So the WebSearch tool. We take the plan and the query, and that returns some research outputs. So that's what we've called outputs there. So next we run the integration agent, and we're feeding various arguments into the integration agent. So the first one is the query, which is obviously the user query, the plan, which is the plan determined by running the planning agent, the output. So this is the result of the output from using the tool. And then the reason. So the reason here is any reason that it might have, the integration agent might have, the last response from the integration agent might have been rejected. So that's after going through the quality assurance process. So obviously on the first run, the reason is going to be blank. And it might not, if there isn't any, if it doesn't get to the point where we actually go to the quality assurance agent, because, for example, we need to step back into the planning agent before delivering a final response, the reason is also going to be blank. And then we have feedback. So that's the previous responses that the integration agent has delivered, and we feed that in from the feedback file. So remember, we get this from the memory.json. And the reason we have that in there is so that when we run the integration agent, it's aware of things that it's already said. So it might try something new or it might adapt it. So it's just to give it an awareness of, okay, I've already given this feedback. Maybe I need to adapt that feedback and do something else if it's not worked. It's something along those lines. It's not exactly like that, but it's just to give it an awareness of stuff it's already tried. Okay. So once we have run that integration agent, we save the feedback, or we save the response from the integration agent to the memory.json. And then we check the response. So this checking response is the quality assurance bit. So it's checking to see that it meets the criteria. And we see if it meets the requirements here. If it meets the requirements, we return true. If not, we return false. And then we get the reason. And then if it is false, we re-enter this loop. So if it is false, we start again and we re-enter this loop of, well, it's not met the requirements yet. And remember, the reason is fed back to the integration agent. So you can see that there. So the reason is fed back into the integration agent. So this will continue as long as we have not met the requirements and we're under the number of iterations that we specify. And that's it. That's putting everything together. Next, we are going to jump into a demo and we're going to test it out with a few questions. So we'll do one basic question and then we'll do one multi-hop question and see how this custom web search agent performs with the open source Llama 3 8 billion model. By the way, this obviously can work with any model on Ollama. You are limited very much by the spec of your computer because it's all running locally. So I'm limited to using the Llama 3 8 billion model. I can't use anything more powerful than that because it's just simply too slow. But if you have more powerful machines, then you can go ahead and have as much fun as you like with the models available to you from Ollama. All right, let's look at that next. Before we get into demoing the agent workflow, I want to talk to you a little bit at a high level about the setup. So I'm not going to go through all of the setup steps now for Ollama, but what you'll have to do is you'll have to go to Ollama and actually download the Ollama server and host that on your machine if you haven't already. There is an option for Windows, Mac, and Linux, so just choose the right one for your machine, obviously. Once you download that, you have to also download the models. So in the GitHub repository for this code, if you read the README, I have provided instructions that you can follow to download the models that you would like to use with this. And remember that this project can be used with any model on Ollama. You're only limited by the spec of your machine. So obviously, if you download a model that is too large for your machine, you're never going to be able to run it. So you're only limited by the spec of your machine. So yeah, that's it. Remember, once you have downloaded the Ollama server, do not change anything here apart from the models. So you can select which models you are using from the Ollama server. And that's really easy to do. Ollama makes it quite easy to select those models because all you need to do is look at the list of models available from Ollama and choose the one that you want to use. All right, so that's it for the Ollama setup. Let's get into the demo for the agent. Okay, so let's try out the agent. And we're going to try it out with Llama 3 Instruct, first of all. I'll try it with a variety of models to see how well each of the Ollama models works. Obviously, Llama 3 Instruct here is the 8 billion version, so it's just a small model. We'll start off with a simple question, and then depending on how well it performs on that simple question, we'll either go into something more complex or we will move on to a different model to see if the model can perform better than Llama 3 Instruct. I would say stay tuned here because I think there will be some surprising things here in terms of which models work well with this type of agent workflow and which don't work so well. So stay tuned and you should be able to learn something new. Okay, So you can see here, we've set the model to Llama 3 instruct. I'm going to bring in my PowerShell. So I'll move that to the side. So let's kickstart the agent by running python agent.py run. Okay, and we'll start off with something simple. What the population of NYC? So if you're not used to using Ollama, Ollama is running totally locally, so 100% local on your machine, which means that it is slower, right? And that's because you are having to download the large language model onto your machine. It's operating on a server on your machine that is actually running on the CPU. Unless you specify otherwise for it to run on the GPU, it's running on the CPU. And large language models are actually optimized to run on GPUs. So that's why if you're not used to using Ollama, it might seem slow to you. That's the reason. It's because it's running locally on your machine. So we have stepped into the agent workflow now. The planning agent has come up with its plan. It says, I'm not going to answer the question yet. Instead, I'll generate some questions that can help me get closer to the answer. And here they are. So it's identified the most important question. What's the city's name that is commonly referred to as the Big Apple and is located on the east coast of the United States? Now, that is completely superfluous. I'm not sure why it needs to know that. That's ridiculous, actually. So we already know we're going to go down a long and mysterious rabbit hole here. And then it's what is the metropolitan area population of the city I'm referring to, according to the latest available data from a reliable source, okay? And then, is there a specific date or year for which you would like to know the population of the city? If so, please provide it. Are there any specific categories of population you're interested in knowing about? Total population, population density, etc. Okay, so we've already established that we're off on the wrong foot because what we have here is the search query. What is the city's name that is commonly referred to as the Big Apple and is located on the east coast of the United States? So we're going to search that in Google, which is ridiculous. We don't really need to know that. And we can see we've run the search and we've returned some results. We've returned a search engine results page. And we've picked out one of those. We picked out one of those pages. So the one we picked out is the top one, Wikipedia wiki big underscore. Oh no, it's not the top one. Apologies. It is the New York Wikipedia article. So is it any of these? New York City, that's Big Apple. Big Apple Wikipedia nicknames of New York City. It's not that one. It's not that one either. So it kind of appears to have hallucinated this, because I can't see this in any of the results returned here. So it's appeared to have hallucinated that response, which isn't good. It's not good at all. That's not what we want. We want it to pick one of these. So we're off on the wrong foot already. And somehow, you know, it's hallucinated it, but it's actually provided the right response. And then we have the integration agent. So based on the provided research, I found this metropolitan area surpassed 10 million mark in the early 1930s, becoming the first megacity in human history. Okay, this suggests that the population of New York City, NYC, has exceeded 10 million people at some point in time. However, I couldn't find a specific date or year mentioned in the research. To provide more accurate information, according to the United States Census Bureau estimate for 2020, the population of NYC is approximately 8.4 million. Please note that this response is based on the provided research and may not reflect up-to-date or exact information. If you would like me to generate further questions to clarify the answer, I can do so. Here are my previous responses. So there are no previous responses, obviously. And here's today's date. So it's just giving us, you know, stuff we prompted it with, but there are no previous responses. Shall I proceed with generating questions or provide more information based on this research? So right now, this response should be checked by the QA agent, and it says it meets the requirements, which is completely untrue. It doesn't meet the requirements. There are no sources there, which is part of the requirements. So I think from a agent perspective, Llama 3 instruct has actually failed that task. So I'm not going to go on to test Llama 3 instruct on anything more complex. I have tried Llama 3 various times before shooting this video, and I can say that I haven't managed to get it to work very well. So we're going to try a different model. Let's try. So let's have a look at the models available to us. So I have previously run some code to actually identify all the models I've downloaded locally. So I'm just going to pull that up again, just so you can see it. Here we go. This is what we want. Get rid of this, get rid of that, and get rid of that. So this is the code you can run. You can run this code request to pull all the models you have locally in Ollama. So I like to run it in Git bash. So here is all the models we have. So we have the Orca 2 model, the 7 billion version. We can give that one a try and see what happens, but I somehow doubt it's going to do any better than Llama 3. What we do have, interestingly enough, is Code Llama 7B. Now, some of you might be wondering right away, why would you run it on Code Llama? And there is a good reason for that. Because Code Llama is trained on code, there's a lot of logic and reasoning inherent in code. And, you know, I've heard quite a few people mention that some of these coding models can make good agents because of their reasoning capabilities. So I'm going to pick that up. I'm going to pick up the Code Llama instruct, which I've already downloaded. We're going to see how well Code Llama works with the agent. So I'll put up the agent. I'll change the model. So instead of using the Llama 3 instruct, let's use the Code Llama model. And I'm going to hit save on that. So remember, this is a 7 billion parameter model. So it is a smaller model, but it's trained on code, or trained for code generation rather than trained for, you know, chat and conversation like the Llama 3 8 billion instruct. So let's go with that. So I've hit save on that. Oh, let's do that again. Hit save. And I'm going to reopen my PowerShell. And then I'm going to say Python agent.py run. Apologies, because that is PowerShell is being formatted in a strange way. But you can see we can enter the query. So let's ask the same question. What is the population of NYC? So let's give it some time to enter the workflow. By the way, if you're curious to see how much resource your Ollama is actually consuming, you can open your processes on your laptop or your computer or whatever you're using. If you're on Windows, it's obviously opening the task manager, and you can see how many resources or what percentage of the CPU your Ollama server is actually consuming when you run this workflow. So we have the planning agent. It's identified some questions. What is the current population of New York City, including both residents and visitors? How has the population of New York City changed over time, and what factors contribute to these changes? Can you provide data or statistics and demographics of NYC's population, such as age, race, and so on and so forth? What are some of the trends and patterns in NYC's population, and how might these impact the city's economy infrastructure? So it has identified some questions, and we've got a search query, population of New York City. So far, so good. Although we have failed to actually retrieve the search engine results page, which is not necessarily to do with the agent, but more to do with the API itself. So let's see if we can kick that back out. So it's timed out. Let's see if we can enter that again. So we have successfully done that. And right, so we've received the search engine results page. You know, and our query is population of New York City. We've selected a best page. So the best page is the wiki. And yep, great. The wiki is actually at the top, which is fantastic. That's exactly what we want. We scrape the results. And then the integration agent has provided something. So according to the information provided, the population of New York City is approximately 8.4 million, with over 6 million residents and 2 million visitors. However, it's important to know that this number can vary on how one defines population and what sources are used to gather the data. So funny enough, and maybe surprising to some of you, Code Llama has actually responded with the correct responses. Well, I don't know if they're correct. Let me rephrase that. It's responded with an answer that seems to make sense. The problem is it hasn't provided a citation for the source, which is bad. We need that citation because then we can kind of double check where that response is coming from. So it's not provided a citation. And the other thing it's done is it says the response meets the requirements and it's marked that as true. Whereas in this case, it's not actually true because it hasn't provided the citation. So that's a problem. That's a problem with Code Llama. So I would say this seems to have worked well on the surface. It hasn't provided the citation, obviously, but for a 7 billion parameter model, and for a model that's not designed for this, it's designed for generating code, this seems to work quite well. And that might be surprising to some of you. So I'm going to try again. I'll try again with a different question. But I think what I'm going to do is I'm going to adjust the temperature. So the temperature is set to 0. But just for the integration agent, I have a gut feeling that if I adjust the temperature for the integration agent, let's put it to something like 0.3, it might actually be more successful at generating the citation or including the citation, let's say. So let's try that. Let's try Python. And apologies again, because the way this has been formatted, it's appearing in a funny place on my screen. So Python agent.py run. Okay, so we're back in. And this time I'll try it. What is the population of Lagos, Nigeria? Let's try that. So again, we are using Code Llama. The planning agent has come up with a question. What's the population of Lagos, Nigeria? We're putting that in the search engine, which is good. Okay, so we have actually returned the search engine results page. And we have identified the best page as the Wiki Lagos, which is the one at the top. And we return the results. So the estimated population of Lagos, Nigeria is over 9 million. Meets requirements this time is identified as false. And we're going to return a reason. So I think for the next one, I'm going to actually print the requirements dictionary so you can see the reason that it hasn't met the requirements as well. That's going to be useful to see that. So the estimated population of Lagos, Nigeria, is 9 million. However, it's important to know that this number may not be up to date as it depends on various factors such as urbanization, migration, all of that type of good stuff. Okay, fine. Yeah, and here's one of the issues we're having. The response JSON is coming back as a structure that we do not actually expect. So instead of the response JSON coming back as instead of response coming back as how does one estimate the current population of Lagos, Nigeria, it's come back as search engine query. So that's a hallucination in the way that the model is actually generating that JSON. So I think from here, we're not going to have much luck with this approach. So both Llama 3, 8 billion and Code Llama are not the best models to be using with as agents, although we've had a bit more success with Code Llama than we have with Llama 3, 8 billion. So I'm going to put an end to the server. I'm going to stop the server. Or end task. So that should be, we should be coming to the end of that. It looks like we did actually in the end get through to more search engine results pages, but I think we were starting to go down a bit of a rabbit hole. So I put an end to it early. What I'm going to do is I want to actually show you what that response dictionary looks like. So I'm going to print it out. Let us print that out here. So under the check response, so we will print it out. Print the decision dictionary. Yeah, response quality assessment. Let's print that out. Right. Okay. And just to show you that this approach does work, let's see how it works with an OpenAI model. So I'm stepping out of Ollama for the minute, and we're going to step into OpenAI, and we will do it with GPT 3.5 Turbo. So let's do it with a lower spec OpenAI model and see how it works. And let's see if we can get the answer to the New York question along with the citations. Great. Okay. And this time we're going to print out the responses as well. So let's start everything up. Python agent.py run. So we have our query down here. What is the population of NYC? What is the population of NYC? So let's go with that. Notice how much quicker it is because we're using OpenAI. So quick now I'm going to have to actually just scroll up to the top and to give you the lowdown on what we've actually outputted here. So planning agent, it's identified as some questions to answer. So what is the estimated population of New York as of the latest data available or available data? Are there any specific demographic breakdowns or trends related to the population of NYC? How does the population of NYC compare to other major cities in the United States globally? Is there any projected population growth or decline for NYC in the near future? What are the primary factors influencing the population dynamics of NYC? So we've selected the question, population of New York City latest data. So that's the search engine query that we've actually selected, right? We've returned our search engine results page and we've picked up a best page. So we've got this nyc.gov site planning data maps NYC population page, and that is actually the top one. So it hasn't hallucinated the link, which is good. And we have stepped back in to the integration agent. So we're marking out our visited sites and we picked out some information from that site. We step back into the integration agent and it says, based on the information provided by the Department of Planning of New York City, the estimated population of New York City is not explicitly stated in the research. However, the department offers the latest population estimates as well as population projections by age, sex through 2040. To obtain most up-to-date population figure for New York City, it is recommended to refer directly to the Department of City Planning or related official sources. And then we've got a source here, which is the source obviously we've pulled out. And then we've got our response quality assessment. So we've marked it as a pass, or the agent has marked it as a pass, which is true. And then we can see the dictionary. It says it's relevant, coherent, comprehensive, and citations. And we've got a reason here. The reason provides, so the response provides relevant information about the population of NYC, explains that the exact figure is not explicitly stated, but directs to official sources for the latest estimates. The response is well-structured, comprehensive, and includes the citation and source. Okay, So fair enough, I would argue that it's not answering the question, and the question is answerable. So that's with GPT 3.5. Then we generate our final response, which is just basically a regurgitation of what the integration agent last generated. I want to share a few thoughts with you about building agents with open source models. So first of all, I want to talk about Ollama as a tool itself. And I think Ollama is a brilliant tool. It gives people access to large language models. So it really democratizes access to large language models. Really, you're limited by your hardware. So I was only able to test models up to 8 billion parameters with Ollama because of my laptop. My GPU isn't big enough to really use with large language models locally. So I was having to use them on the CPU, which are the models that you use on the CPU with Ollama are quantized models, so they're not full precision. And therefore, that does impact their performance. However, I will say from experience that I haven't found that 8 billion parameter models work well with these types of agent workflows. So that's one of my observations. If you are going to build agent workflows, you probably want to start with some larger models rather than going for the 8 billion parameter models. And if you're working with open source models, if you don't have the specs locally, if you don't have the large enough GPU, for example, you will probably want to think about renting your own GPU and standing up your own inference server. So I'm going to do a future video on this, on how to set up your own inference server and rent through a rented GPU service. I'll do this through RunPod, and I'll show you how to integrate one of the larger open source models with the custom agent that I've built. So keep an eye out for that video because that's soon going to be landing on my channel. The other thing I want to do is I want to test out a variety of those open source models and compare them with the performance of the models from OpenAI and see which open source models do compete with the best of the OpenAI models. So I'll be doing a separate video on that, and I'll be creating a test and I'll run through those live on a video, and I'll show you for each model which one performs the best against those tests compared to the OpenAI models. Now, in terms of improving the custom agent, there are various ways that this could be done. I think the prompts could be optimized a little more. So I wrote those prompts myself, and I haven't put them through ChatGPT or anything like that to try and optimize them. So I think there's opportunities to optimize it. You can play with this yourself because the code is available to you, as I pointed out earlier. I think the approach for selecting websites could probably be changed as well. Really, the thing that makes the biggest difference to the performance is the model you use. So the dream of kind of running things locally for now, for most people, you're not going to be able to build your own local AI agent using the Ollama models available to you for most people, because I gather your laptop is just not going to have high enough specs to run the state-of-the-art models. Until we can get more efficient ways to run those larger models locally, or until we get higher performance, smaller models, I think the state-of-the-art AI agents are really going to be powered by the proprietary LLM services or the largest of the open source models. And when I say largest, obviously I'm correlating that with the best performing too. If you like this content, give us a thumbs up. Let us know your opinions in the comments section. And don't forget to subscribe to the channel for more AI and large language model based content. Thank you once again, and I'll see you in the next videos.